Hello future learners, subscribers, viewers, and students. Here is another video, another solution to this problem here by the conjugate beam method. So this is the original problem. The beam is subjected to the load shown. If EI is constant, determine the slopes and deflections at points A, B, C, D, and E by the conjugate beam method. So conjugate beam method. So the reactions are here from the preceding methods, and selecting point B as the moment center, this will be the loading diagram, which is the moment versus moment over EI diagram. So 107 over 3 times 3 is 107 over EI, 356 over 6 times 6, so 353 over EI, 353 over 6 times 3 at C, 176.5 over EI. Then the moment due to the uniform load, we divide this trapezoidal loading into two parts. One is the uniform 15 kilonewton per meter load, so 15 times 3 times 1.5 is 67.5 over EI, and this is a second degree curve. For the triangular loading, 1/2 of 3 times 15, 30 minus 15 is 15 also, times 1, so 22.5 over EI. For this point load, 12 times 3, 36 over EI. And for this another point load, 15 times 8, 120 over EI, 15 times 5, 75 over EI, 15 times 2, 30 over EI. So this is the complete loading diagram. Then we transform this beam into an equivalent conjugate beam. So the end support, which is a pin, remains a pin. This interior roller support becomes an interior hinge, and this free end becomes a fixed end. And the loading should be this M over EI diagram. So this is the analysis. First, we find theta A. This, by the way, these are the positive directions of slopes and moments, considering the segments later. So theta A, then this is theta D, going down the positive direction. So considering AD, we sum up moments about D first to solve for theta A. So this is the equation, theta A times 9 plus 1/2, 3 times 107, this is 1 plus 6, so 7, plus 1/2 of 6 times 353, 2/3 of 6 is 4, so 1/2 6, 353 over EI times 4, minus the moment of this second degree area, so 1/3 of 3 times 67.5. The location of the centroid from this leg is B3 over n plus 2, so 3 over 2 plus 2 is 3/4 or 0.75, so its distance from D is 6 minus 0.75, so 5.25 meters. Then minus the area of this third degree diagram, 1/4 of 3 times 22.5 over EI. This distance is 3 over degree plus 2. 3 over 3 plus 2 is 3/5 or 0.6. So its distance from D is 6 minus 0.6, so 5.4. Then minus the moment of this triangle, 1/2, 3 times 36. The moment arm, because this is 1 meter, 1/3 of 3, so that would be 5 meters. Okay. Then for this trapezoidal loading between A and D, so this is trapezoid. Let's break this into two triangles. First triangle with height 30 over EI, so minus 1/2 of 6, 30 over EI times 2 meters, 1/2 6 30 over EI times 2, and lastly 1/2 of 6 times 120 over EI, 2/3 of 6 is 4. So solving for theta A is negative 336 over EI, just like before. Next, we consider AB to solve for theta B and delta B. These are the positive direction. If we consider AB, at the right section, shear is going down positive and moment is counterclockwise. So summation forces Y to solve for theta B. Theta A plus 1/2 of 3 times 107 over EI equals theta B. Theta A, negative 336 over EI plus 1/2 of 3 times 107 over EI equals theta B. So solving for theta B, it is equal to negative 175.5 over EI, just like before. Then summation of moments about B equals 0, counterclockwise positive, so we have delta B is delta B counterclockwise equals clockwise moment. So delta B equals theta A times 3 plus 1/2 of 3 times 107 over EI times 1. So delta B is theta A times 3 plus moment of area of triangle 1/2 3 107 over EI times 1. So solving for delta B is negative 847.5 over EI. Then having found the deflection and slopes at B, we next consider CD. But before we consider CD, let's solve for theta D. To solve for theta D, we go back to AB and we sum up forces vertical equals 0. So let's go back to AD and sum up forces vertical equals 0. So theta A, negative 336 over EI, plus 1/2 of 3 times 107 over EI, plus 1/2 of 6 times 353 over EI, minus 1/3 of 3 times 67.5 over EI, minus 1/4 of 3 times 22.5 over EI, minus 1/2 of 3 times 36 over EI, then minus we'll just treat this as trapezoid. So minus 1/2 of quantity 120 over EI plus 30 over EI times 6. What's that? Then equals, or minus theta D equals 0 or equals theta D. So solving for theta D is 295.125 over EI, just like before. Now we consider CD. Then this is the positive slope at C for shear. This is upward, that's the left section for section CD. And moment or delta C is clockwise if C is the left section. So summation forces Y equals 0, theta C plus this area 1/2 of 3 times 176.5 over EI, then equals downward areas. So I'll treat this as trapezoid, so equals 1/2 of quantity 75 over EI plus 30 over EI times 3. This is it. Then plus theta D. And theta D is 295.125 over EI. So computing for theta C is equal to 187.875 over EI. Then for delta C, summation of moments about C equals 0 considering CD. So delta C, which is this, then minus, let's split the area of trapezoid into two parts, triangle and another triangle. So delta C clockwise about C, then minus 1/2 of 3 times 176.5 over EI times 1, the moment arm, then plus for this small triangle 1/2 of 3 times 30 over EI times 2, then plus this bigger triangle 1/2 or 3 times 75 over EI times 1, then plus theta D 295.125 over EI times 3 equals 0. So solving for delta C is negative 823.125 over EI. Then finally for DE, this is now the free body diagram. Let's consider DE. So first, we already know theta D, so we can solve theta E by summing up forces vertical. So upward equals downward. So upward theta D 295.125 over EI equals downward theta E plus this area 1/2 of 2 times 30 over EI. So solving for theta E is 265.125 over EI. And finally, for delta E, this is the positive sense of moment or deflection by conjugate beam. So summation moments about E equals 0, counterclockwise positive. So delta E plus the moment of this area 1/2 of 2 times 30 over EI, and that distance is 2/3 of 2 or 4/3, then equals theta D times 2. So equals 295.125 over EI times 2. So solving for delta E is 520.25 over EI. So that's it for this video.